So the state of diagnostics for Lyme disease, so I really want to just keep my talk very, very short because what I'm about to say is just basically the state of diagnostics for Lyme disease sucks, and we need better testing. And I think that what I can do to say more about that is actually to introduce you to someone, actually to a group that is we are working with to try to solve that problem. And I think at the end of all of these conversations today, which are terrifying, okay, so Borrelia causes long-term persistent infections that lead to chronic inflammation, which causes long-term diseases. We have Bartonella, oh my God, you know. And the fact that we have no clinically accurate diagnostic test for Lyme disease at this point is criminal, in my opinion. We've been working on this disease for over 30 years, and so it's time that we start applying technologies that exist in other areas and trying to come up with a better way to detect people who have the diseases. And then once we actually can identify people who have the disease versus those that do not, then we can start to do clinical trials on patients that have Lyme disease versus people who do not. And I'm going to add to that now that we have talked about it. Not only do we need an accurate diagnostic test for Lyme disease, we need an clinically accurate diagnostic test for Bartonella, we need a diagnostic test for Anaplasma, we need a diagnostic test for all of them. And so that was my message. That was going to take about 20 minutes, and I just said it, so I hope that's going to be okay with everybody. So what I would like to do now is to introduce you to somebody who will talk about a technology that we hope will be the technology, or at least will help advance this issue. So I would like to introduce to you Dr. Kathryn Sykes, who is the Vice President of Research at HealthTel Incorporated, a company that develops products for comprehensive biological measurements based on an immunosignature technology. Her previous research at Arizona State University's Biodesign Institute and University of Texas Southwestern Medical involved the discovery of molecular, bead, and array-based approaches to enable novel vaccine discovery and the engineering of combinatorial screening for protective antigens for infectious and chronic disease. And from that work stems what they're working on now. And so I'll just introduce you to Kathryn Sykes.
Thanks, Holly. Thank you very much for the invitation, Jessica and Tammy, and thank you very much, Holly. We don't study any disease at all, so what we really are at HealthTel is molecular technologists. So as Holly alluded to, I'm going to tell you about one that was actually invented by Stephen Johnson at ASU, who's sitting at that table over there. And actually, I'm going to show you a very initial experiment that he did with Tammy and Jessica, I think last year, and I'm going to direct you to him for some of those details. But Stephen and I work very closely together, and HealthTel, the company that I'm at, is actually a spin-off from his work at ASU. So the big green one, okay. Let's see. So the first thing I want to do is kind of explain the technology a little bit. And that's what, I'm going to tell you what the concept was that Stephen invented and how the test is actually done, and then how the analysis is. And then I'm going to show you a few examples and why we think this might be applicable and a new avenue for Lyme. So this is a cartoon that describes the concept. And I want to point out with the, here we go, good. So any sort of biospecimen that has antibodies in it can be used, typically a serum or plasma or a whole blood sample. And it's placed on a surface that's actually a silicon wafer, just like Intel has. But we've layered peptides in situ and built them into long strings of peptides instead of an integrated circuit. This biospecimen is placed onto these individual features. Now, this is represented as a single peptide, but actually each feature may have tens of thousands of peptides of the same type at each individual feature. The libraries that we use have anything from 100,000 to 3 million features, depending on what our need is. So antibodies were selected because they amplify by the health state. No, we talked a lot about PCR. PCR is also an amplified detector molecule, but it's amplified by a researcher. Antibodies are amplified by the biological state. So Stefan chose that as an ideal detector molecule. But that doesn't make this unique at all. Serology is around. However, a couple unique concepts are the peptides on this surface are diverse sequences. They do not map to any biological space. So it's a sampling of combinatorial space. And what that means is the antibodies, when they're laid on here, have to choose between all this possible diversity that's much more expansive than what is available in biological space. And another feature of this concept is that the binding of all these antibodies are simultaneously being competitive. So unlike in ELISA, where everything happens in one dish or the next dish or well, the next well, it's all happening at the same time. And then those results are analyzed, and what you get is this fluorescent pattern that's different depending on the biological state that represents the difference in the antibody repertoire of that particular health state. And algorithms can be developed that inform differences or commonalities between any two or more health states. As you can see represented here, this feature exists in cancer, but not in the other two states, and so on and so forth. Final concept, this is going to spend the most amount of time on this slide because it presents the whole concept. Last concept is, as represented here, a binding event can exist as an up or a down, and as a difference relative to some other contrasted health state. And that makes it also different from, let's say, an ELISA. So this is just really quickly show you the silicon wafers that we use to build up the peptides in situ. We then cut them, dice them into something that looks like a microscope slide, so we can use standard equipment in the lab. And then actually we even assemble them into a pretend ELISA plate, so we can use all the standard equipment as the workflow. More recently, in the past about year or two, we've actually moved into a customized Hamilton integrated system that we're able to scale massively, and actually right now we have 3 of these. So, by the way, we're down the road. We're in Chandler, in case anybody didn't know that. Historically, we are in the original Intel building when they moved over from California in the 70s. But, so this is how final on the sort of technology, how it's analyzed. The fluorescence that from detecting the antibody binding on those silicon wafers is the readout. And that data is processed and transformed. And then what is, look, how do you go backwards? That's probably the red one? The red one. Okay. We just do something like a simple Welch's t-test to see differences between the peptide intensities up or down. It's very quantitative. It's not binary. Between any particular contrasting groups. Then machine learning algorithms are employed. We've tried many of them. We usually use SVM. And then you do an estimated performance within your training group. So you need a training group, and then you you validate that performance in a completely independent cohort. And that's a standard machine learning activity. So now I wanted to show you some of our data, and then also show you the preliminary experiment that Tammy and Stefan did at ASU, although he should be presenting that, not me. Now, I thought I should give you an infectious disease, but now I'm thinking I should have done the cancer. But I did pick Chagas, which was actually brought up earlier in the day about trypanosomes. But I picked Chagas because there is a lot of parallels between Chagas, which is a chronic disease, and Borrelia. It's located in endemic areas where the insect vector is found. It has multi-host life cycle. It has many immune evasion mechanisms. Diagnosis by serological tests is required because detecting the parasite itself in the blood, it can only happen in a very short period of time during an acute phase. And there are lots and lots of challenges in detection, disease activity, severity, and prognosis. This is actually this work is published about a year ago, but I'll just briefly kind of just show you how we conduct an experiment, how we get to our diagnostic. Our hypothesis was that this platform could provide something new relative to a diagnostic biomarker based on these antibody binding to these diverse arrays. This is the two cohorts that we use to identify our diagnostic test. The training cohort had both seropositive and seronegative T-Cruzi blood donors, which we actually got from Creative Testing Solutions, which is also down the road here in Tempe. And this is just to show you what the cohort looked like. It was quite a large group that had both positive and negative donors, and this S/CO is the signal to cutoff. It's basically a measure of the ELISA titer that was used by the blood bank testing panel to determine positivity of T-Cruzi. And this was a completely independent group of 58 negative and 58 positive that we eventually tested our algorithm on. This is what the data looks like when you plot it relative to basically the fold increase in intensity relative to the significance of that increase. And all of these above this line were analyzed to be highly significant. The ones that are colored either blue or green also correlated with the ELISA titer, either higher or lower. But interesting, not all of them did, meaning there was information that overlapped with the ELISA, and there was information here that was uniquely not in the ELISA test. This is what a machine learning algorithm for cross-validation can look like. You do some internal splitting of your group, and then you test on what's left out. And then you take the other 20, then you take another 75% and a different 25%, and you keep retesting to see whether your selection of peptides was good enough to achieve a distinction in your two contrasting groups. And then you repeat that 100 or more times to come up with some sort of estimated performance of you being able to use those peptides in this algorithm to distinguish those health states. This is a raw curve, which has a lot of detail, but I think it shows a relationship between the specificity and sensitivity, and that because this test is quantitative, you can choose what's more important to you, to have high specificity or high sensitivity on this curve. And this was the cross-validation results, and then that algorithm was applied to a completely independent group, and you can see that our area under the curve were very similar. There were overlapping confidence intervals. And what this area under the curve basically means, if you took any one of the, let's say, positively defined individuals from this group, there would be a 98% chance that the ELISA-defined positivity was the same. So I said this was a quantitative test, and you could use the relationship between the sensitivity and specificity in any way that you chose relative to your application or your need. You know, whether it was more important to make sure you picked up every single Chagas patient, or whether it was okay to miss a few and not tell someone they had Chagas who really didn't. You know, that kind of mentality. Well, you can also just define a threshold, a cutoff. And so if we were to do this and just say 50% probability, then you can come up with a binary declaration of either positive or negative for any particular donor. And I wanted to show you this here because we were perfect here. We got all of the positives right. This is the immunosignature result, and this is the blood bank ELISA result. So there were no false positives, but we did get 14 false negatives. And when I presented this to the blood bank, because they had provided the samples, they said, probably not. You guys were right and we're wrong, because on our raw curve, it's really important to pick up every single possible Chagas positive serotest, because that would go into the blood supply, the U.S. blood supply. And we've applied this to different kinds of contrasts. Obviously, I showed you an infectious disease diagnoses, but we could do differential diagnoses. We could do disease activity, patient stratification, and you can read here of some of the other. But I want to zip to Stephan's data, which is right here. And this was done, as I said, by Stephan at ASU and also his colleague Philip's Stafford. So here, Philip was the bioinformatic scientist. So he took these are actually Tammy samples too, by the way. I think it's mentioned up here. So Tammy provided some samples from her repository, and these guys ran it on similar types of libraries that I described to you initially, and contrasted Lyme disease versus healthy, and their area under the curve, their predictive value of whether the FOL's declaration of Lyme versus healthy matched the immunosignatures definition was 0.784, which is quite good. And Phil suggested I point out that you can kind of see this blue here is chronic symptomatic patients. You can kind of see a pattern. Every time you see that blue, you can kind of see activity here, see activity here. And likewise, every time you see that mustard color, whatever that is, these patients are seropositive with Lyme. You can kind of pick that up. So here's another batch of signal. And this is I think I forgot to mention, these are all of the peptides that were used to distinguish the two health states. And over here are the different patients. I apologize for not saying that first. And this is similar analysis with a heat map. But in this case, Phil took samples that were setting up a selection of peptides to distinguish an acute set that he and Stephan had versus some controls. And then that gave him this selection of peptides here. And then he said, okay, where are Tammy and Jessica's samples fall within the signal from those acute defined peptides. Hope that's clear. And what was very surprising is all of FOL's convalescent samples fell right in with Stephan and Phil's acute samples. And the red are the ASU acute, and the yellow are the FOL convalescent, which everybody seemed to find quite surprising and led Stephan to point Tammy and Jessica to us. So we're in the final stages of getting a scientific research agreement in place with FOL and HealthTel. I should skip to here, where we will be using some samples that Tammy has been able to get from Johns Hopkins University. We will then use those samples on the system that I just described to you. And our first goal, I would like to point out, would be to focus on the early stages of the disease and be able to define whether or not a person has Lyme disease versus something else. And that might be Bordetella, that might be arthritis, that might be MS or RA, whatever the community defines as the most important, and I'll stop there. And I left, I put Stephan's contact information down here in case anybody wants to talk to him. So,